What is offshore wind energy and why are we resisting? I'm Elizabeth Robson and I'm with Protect the Coast Pacific Northwest, and I'm concerned about the environmental impacts of offshore energy development in the Pacific Northwest of the United States. This presentation is split into two parts. The first part focuses on the offshore wind energy technology, while the second part focuses on the environmental impacts of offshore wind energy technology. Offshore wind energy areas, or OWEA for short, are clusters of wind turbines and other infrastructure in coastal waters and on the coast shore. On the east coast of the United States, turbines are typically installed on the continental shelf. That is, they're installed directly onto and into the seabed. On the Pacific coast in the Pacific Northwest, the continental shelf drops off quickly, so turbines will be floating offshore wind energy areas, or FOWEA. Floating turbines sit on floating bases, which are anchored into the seabed with long cables and drag anchors. Other components of offshore wind energy areas include offshore and onshore substations, electrical cables, onshore maintenance hubs, grid lines, and more. Floating turbines are a relatively new technology, but large areas of floating turbines are planned for the Pacific Northwest as well as the Gulf of Maine, with little understanding of their impact to marine ecosystems. I live in the Pacific Northwest, and I'm extremely concerned about the many impacts these turbines and the associated infrastructure will have on the natural world. A website has recently been launched to track offshore wind energy areas, offshorewindpowerhub.org. This is a map of projects under development. Here you can find out the names of the projects, the companies involved, and the status of a project. For instance, off the coast of California, we can see that the Even Keel wind project is in the permitting stage. On the East Coast, we can find the Vineyard 1 wind energy area that is currently under construction by Copenhagen Infrastructure Partners. We'll use this Vineyard 1 project to describe the size of offshore wind turbines currently being constructed. Vineyard 1 is fairly small, although we saw from the map it's right next to many other proposed wind energy areas, so it will end up being part of a much larger cluster of turbines. Vineyard 1 has 62 turbines that are 13 megawatts each, for a total of about 800 megawatts that at peak efficiency could power about 400,000 homes. Now, power companies use the number of homes as a metric to illustrate how much power is generated by wind energy areas. But keep in mind that this electricity will probably not be used to power homes, but rather industry, including rapidly growing data centers. Each tower is 853 feet tall, which is just shorter than the Eiffel Tower at 1,063 feet. Each blade is 351 feet in length, which is about the length of a football field and weighs 60 tons. The swept area of the three blades on a turbine is about 500,000 square feet, which is about the size of 5 city blocks in New York City. The blade tip speeds can exceed 150 miles per hour. Here's a visual representation showing how one of these turbines compares to the Washington Monument, the Eiffel Tower, and the Empire State Building. The expected lifespan of these turbines is about 25 years, as long as they don't fail spectacularly, which one of the turbines under construction at Vineyard 1 did on July 13, 2024. On a calm, sunny day, one of the blades of a turbine in the Vineyard 1 project, currently under construction, completely failed, and pieces of it started falling into the ocean. Remember, each one of these blades is the length of a football field, so this is a significant amount of material falling into the ocean. Large chunks of fiberglass and styrofoam started washing ashore on regional beaches, and Vineyard 1 failed to notify the public until 2 days after the accident, putting fishing vessels at great risk. A representative from Green Oceans, a group fighting offshore wind energy on the East Coast, said, If they build all 9 projects, that is, the projects in the area of Vineyard 1, given the rate of blade failures, 15 blades could fall into the ocean here every year. That would be over 1,000 tons of epoxy, fiberglass, and foam contaminating our beaches and oceans every year. A 747 weighs 200 tons. Do we want the debris equivalent of 5 jumbo jets polluting our waters every year? Globally, wind turbine blades are failing at a rate of about 3,800 a year, which is a lot of debris in the environment. In the ocean, it's difficult to find and retrieve this debris, so any blade failure in offshore wind energy areas is likely to contaminate oceans and coastlines for many years to come. The next generation of offshore wind turbines are even larger than those being constructed at Vineyard 1. Vineyard Northeast is another project in the same area. The turbines for this project are projected to be much larger, capable of generating 15 to 22 megawatts, with a height of 1,312 feet, even taller than the Eiffel Tower, with 500-foot blades and blade tip speeds exceeding 200 miles per hour. Here are some photos of wind turbine staging areas on the East Coast. Ports nearby wind energy areas must be expanded to accommodate staging areas, to receive wind turbine components and prepare them for installation. You can see the massive blades next to the construction workers to get a sense of how large they are and the massive size of the towers. These are the nacelles that sit on top of the tower, where the blades are attached. Each one is the size of a small house. I'll describe in more detail what a nacelle is shortly. I'll now focus on the components and infrastructure required to build floating offshore wind energy areas. As I mentioned earlier, the offshore wind energy areas in the Pacific Northwest will all be floating. So what's required to build floating offshore wind energy areas? The turbine components, including the tower, nacelle, and blades, the floating bases the turbines sit on, the cables and chains used to anchor the turbines, the anchors themselves, substations, both offshore and onshore, to receive, transmit, and convert the electricity, electric cables to transmit the generated electricity to substations, installation and maintenance vessels to service the turbines, and onshore infrastructure including substations, grid lines, ports for vessels, staging areas, and more. This is the infrastructure directly related to the wind turbines. And of course, there is a lot more infrastructure required to build wind turbines throughout the supply chain, starting with the mines to extract the materials used to build turbines and all the related infrastructure, the refineries, the ships and trains and trucks to transport the materials, the factories where the components are built, and so on. To give you a sense of what's required to make one of the steel towers used for a 15 megawatt wind turbine, you need 3,250 tons of gray steel. Each ton of steel is responsible for between 1.4 and 3 tons of carbon dioxide equivalent emissions, which is 4,550 to almost 10,000 tons of CO2 equivalent per turbine tower. Advocates say wind energy is clean and green, but 720 to 800 pounds of coal is required to make 1 ton of pig iron that is then eventually used to make steel. And that's 1,300 tons of coal per turbine. I don't think of coal as clean or green. At 1.6 tons of iron per ton of steel, that's 5,200 tons of iron per turbine that must be mined from the earth. Steel can be recycled, but that requires up to 3,000 degrees Fahrenheit to melt and refine. And it is an energy-intensive process. And again, just to reiterate the size of the towers, they're huge. That's why they require so much material. The nacelle, the structure that sits on top of the tower, is typically over 50 feet long and can weigh more than 300 tons. The nacelle contains a gearbox and generator, electrical components that require about 14 tons of copper in a 15 megawatt turbine, and of course that copper must be mined. The nacelle generator includes magnets made out of rare earth elements. These elements are mined and refined primarily in China, where it is devastating the environment. And each nacelle contains about 800 gallons of oil and lubricants. Just to remind you of the size of the nacelle, here's a photo of the nacelle, and here's a diagram showing the main components of a nacelle. And here's a photo of a rare earth mine in China. It looks like a typical mine. And oil leaks from nacelles are fairly common. This is bad enough for the onshore environment, but can be extra deadly in the marine environment, where even just one drop of oil can damage a marine bird's water-repelling feathers and kill them. Now let's talk about the blades. There are typically 3 blades on a wind turbine, and remember that each blade is 350 feet or more in length. Blades are made out of fiberglass, which is made out of plastic and glass and composite materials, balsa wood and styrofoam to provide a rigid structure to support the fiberglass, and resins and epoxy to glue it all together and protect the blade from rain, seawater, and so on. This diagram shows the various components of a blade and how they're structured. Fiberglass is a major component of wind turbine blades, and it's made from glass and polymers. To make fiberglass requires mining quartz, melting the quartz at high heat, extruding the glass into fibers, and coating the fibers with polymer resins. The balsa wood used to create blade structure is logged from the rainforests of South America, primarily in Ecuador. The demand for balsa wood is decimating balsa forests, so increasingly blades are also using styrofoam to create rigid structure. We all know, of course, that styrofoam is a fossil fuel product. It's not recyclable, and it's devastating if it gets into the environment. This is a photo of some of the styrofoam found along the beaches after the blade failure at Vineyard 1. When a blade fails, not only does it pollute the environment, it can also be extremely dangerous. Here is a short video of a blade failure on an onshore wind turbine. In this case, the entire wind turbine collapses. If this collapse happens in the ocean, the wind turbine components like the nacelle and the tower pieces will sink and create an oil spill and other contamination that will be very difficult to clean up, if at all possible. An issue with wind turbine blades is leading edge erosion, where the epoxy, glue, resins, and paint covering the blades erodes over time. This spews contaminants, including microplastics, into the environment. One estimate concluded that one turbine can erode 62 kilograms or 136 pounds of microplastics into the environment per year. For a large wind energy area like those being proposed for the West Coast and constructed on the East Coast, this would result in thousands of pounds, many tons, of plastics and other contaminants entering the environment every year per wind energy area. We know that the steel in the towers can be recycled, but what about the blades? These cannot be recycled. They can be downcycled, but typically they're landfilled or burned in concrete plants. Those that are recycled are downcycled into plastic fabric, or the blades are chopped up and used as aggregate filler for infrastructure like roads. An offshore turbine must sit on a base. On the East Coast, these bases are installed into the seabed, typically on a monopile base that is pounded 150 to 200 feet into the seabed. Each monopile is about 40 to 50 feet in diameter. On the West Coast and the Gulf of Maine, where floating offshore wind energy areas are planned, the turbines will sit on top of floating bases. For the largest turbines, the bases can be about the size of a football stadium, and these bases must be anchored to the seabed with long chains and cables to keep them from moving away and to keep the turbines from toppling over in storms. This diagram shows the various bases used for wind turbines. The most typical base for a grounded turbine is the monopile, and it remains to be seen which of the floating turbine bases will be used on the West Coast, but most of the floating turbine photos I seem to see use the barge base type. Here's a photo of one. The cables, chains, and anchors required to stabilize a floating wind turbine are massive, as you might expect for a machine the size of the Eiffel Tower on a base the size of a football stadium. A British report about the materials requirements for floating turbines states that for an offshore wind energy area of 132 floating turbines, 15 megawatts each, what would be needed is 528 mooring lines, requiring 238 kilometers of chain made out of steel, 30 kilometers of rope made out of plastic, over 1,000 clump weights to help sink and stabilize the cables and chains, 396 drag anchors, and 132 suction anchors, among other infrastructure. Just imagine the massive amount of material required to make all of this, and the impact mining and constructing these components will have on the environment. I don't know if emissions life cycle analyses of wind turbines takes these components into account. This is a diagram showing some of these components. Here you can see the anchor, the clump weights to hold down the chains, the mooring lines, and so on. This diagram shows different ways the mooring lines can be used to hold a turbine and its base to the drag anchors. And this conceptual illustration shows the whale's eye view of a wind energy area. Keep in mind that many of these wind energy areas will consist of hundreds of wind turbines, creating what some call a labyrinth of death, a labyrinth of cables that marine animals must navigate, which may quite possibly disrupt their migration, their breeding, their feeding, or even kill them outright. Again, floating wind turbines are very new, so almost no research has been done on the impacts to marine environments, and yet corporations and government agencies are proceeding with these plans. This photo shows the size of the chains used to stabilize offshore infrastructure. Each link is massive, and remember that many hundreds of kilometers of chain are required for 132 15-megawatt turbines. Now imagine the chains required for thousands of wind turbines all along the coastlines of the US and around the world. This is what a drag anchor looks like. It's difficult to tell how big it is in the photo. It's huge. This is what's embedded in the seafloor, and I'm sure you can imagine the impacts that will have on the seafloor. This photo shows a drag anchor being installed so you can get a sense of how big they are. One major concern with floating offshore wind turbines is the sediment plumes that will result from chains dragging along the seabed as the base and turbine move with the wind and waves, and especially in storms. Dragging chains will result in the death of marine life who live on the seabed, and large sediment plumes disorient and kill marine life who normally live in and rely on clear water to survive. Next up is substations. Offshore substations collect AC electricity from the wind turbines. Multiple turbines are connected to one substation. The substation converts the electricity from AC to DC for transmission on high-voltage electrical cables to the mainland. High-voltage direct current, or HVDC, is more energy efficient than AC with lower loss of electricity over long distances. The HVDC cable is connected to an onshore substation, which then connects to the grid. Substations must be moored, just like wind turbines. Floating substations are moored with cables, chains, and anchors. The number of substations per offshore wind energy area depends on the number of turbines. Vineyard Wind 1, with 62 turbines, is using one substation, but a larger offshore wind energy area will need multiple substations. Aside from the materials required to build substations, impacts from substations include the potential leaks of SF6, a gas used to insulate electronic components. This gas has 23,500 times the atmospheric warming power of CO2, so even small leaks can make a big difference. Another issue with substations is that they often use cold ocean water for cooling. They take in this water, cool the components in the substation with it, and the water absorbs the heat. The water dumped back into the ocean can be as hot as 90 degrees Fahrenheit, far hotter than ocean water, and so would have an immediate impact on marine life in the area. Biocides are added to the cooling water to prevent algae buildup in the cooling system. Substations must have backup batteries or generators in case no power is being generated by wind turbines. This image shows an offshore wind energy area with cables connecting to an offshore substation and an HVDC cable connecting the offshore substation to an onshore station. This image shows the size of a typical substation. As we saw in the previous images, electrical cables connect from each wind turbine to a substation and then from the substation to an onshore station. The cables connecting the turbines to a substation are known as array cables, and the HVDC cable connecting to the onshore station is called an export cable. Array cables may or may not be trenched, but the HVDC export cable usually is. They are buried 6 feet into the seabed and covered with sediment and rocks. This is done using a cabling vessel and a jet sled, also known as a hydroplow, which digs a trench and lays the cable. Rock installation vessels are then used to cover the cables. Here's an image of a jet sled. As you can see, it's quite large. This diagram shows how the cable is laid using the cable laying vessel and the jet sled. Cable laying and rock installation vessels are two of the many specialized vessels required to install offshore wind energy areas. These vessels collectively are known as Wind Turbine Installation Vessels, or WTIV. As of 2023, about 25 to 30 vessels for offshore wind have been recently delivered, are under construction, or are on order from U.S. shipyards. The demand for wind energy areas is increasing demand for all the other infrastructure, equipment, and vessels and other machines required to install wind energy areas. Vessels required include vessels to transport and install wind turbine components or tow a floating wind turbine on its base into location, survey vessels, crew transfer vessels, heavy lift vessels, rock installation vessels, and service operation vessels. Here's a photo of a wind turbine installation vessel. This can be used to install wind turbines onto monopiles, like the kind of turbine used on the East Coast. As you can see, once the vessel is in location with all the parts, it lowers its stabilizing legs to the seabed and raises the vessel above the water to prevent the vessel from being moved by the ocean while installation is being completed. To give you a sense of how large this ship is, remember that the tower is the size of the Eiffel Tower. This is an illustration showing the various vessels used to build offshore wind energy areas. So far, I've described the offshore infrastructure required to build offshore wind energy areas. Onshore infrastructure is also substantial. Where the export electrical cables come ashore from offshore substations, these cables must be trenched into the shoreline to the onshore substation. An onshore substation must be built. New grid lines must be installed. Ports must be built or expanded to support the many specialized vessels, large components, and machines required to move these components into the support areas and onto the vessels. And of course, the roads into the port must be large enough to transport the huge components of wind turbines and other related components. The workers at the port, including installation as well as service crew, need housing. And of course, let's not forget the many mines, refineries, and factories that must be built to extract, refine, and process, and then manufacture all the components and equipment required for offshore wind energy areas. I hope this has given you a sense of the massive undertaking that an offshore wind energy area entails. Offshore wind energy areas are huge industrial energy projects and require large amounts of materials, massive machines and ships, and electrical infrastructure to support them. It should be clear to you that the offshore wind industry will have a huge impact on the environment, both the marine environment affected by the turbines, chains, anchors, substations, and installation and maintenance vessels, as well as the onshore environment impacted by expanded ports and new grid lines. A recent article in Hakai magazine, which is a magazine about the environment and ecology, announced that environmentally offshore wind is fine. The article describes some of the many incredibly harmful impacts of offshore wind turbines, but concludes that, yes, it's fine. I highlight this article because of a quote in the article which says, "To hit the world's climate goals, projections suggest the world's offshore wind capacity needs to scale to 2,000 gigawatts by mid-century. That would mean installing a whopping 5,000 new turbines in the ocean every year for the next 25 years. That would be a total of 125,000 wind turbines and all of the associated infrastructure I've just described. Remembering that 132 wind turbines require 238 kilometers of steel chain, 125,000 turbines would require 225,148 kilometers of steel chain. That would be enough steel chain to circle the Earth almost 6 times. I'll leave you to do the math on how much copper, iron ore, nickel, coal, and other materials would be required to build 125,000 turbines. This is the end of part 1. I'll cover the impacts on the marine environment of offshore wind energy areas in part 2.